Wherever possible, engine components are made of materials with a high heat conductivity. Most air-cooled engines have cylinder heads which are machined from forged aluminium alloy. The cylinder heads are heated, and while they are still hot, they are screwed onto alloy steel cylinder barrels. It's common on some high-power engines to make the exhaust valve stems hollow, and to partly fill the space with sodium. At normal engine working temperatures, the sodium melts, and with every movement of the valve, the liquid sodium is projected from the hot valve face end to the cooler valve tip. This facilitates the dissipation of heat from the hot part of the valve to the cooler part. The cylinder head temperature gauge is an engine instrument designed to aid the pilot in protecting the engine against its enemy, excessive heat. The operation of the cylinder head temperature gauge is dependent on a probe, which is mounted on the engine cylinder head. This probe sends a voltage, which is proportional to the temperature of the cylinder head, to a gauge in the cockpit. The gauge in the cockpit is a millivoltmeter, which has been calibrated in either degrees Celsius or Fahrenheit. Most general aviation aircraft engines sample the cylinder head temperature of the hottest cylinder. The hottest cylinder is determined by extensive flight tests carried out by the engine manufacturers. The cooling arrangements for any particular type of engine are designed to ensure satisfactory cooling during cruising flight, when the forward speed of the aircraft should give an adequate flow of cool air. It is a fact, however, that aircraft go through many different stages of flight other than just the cruise, when the airflow pattern will differ from the cruise standard. The following information may assist the pilot in determining the best procedures to be employed when using the engine cooling system. At high power settings and low airspeed, such as those experienced at takeoff, the cowl flaps should be selected open to increase flow rate of air and so increase cooling. When selected to this position at takeoff, the protruding cowl flaps may increase drag. During a climb, when high power is being used, high temperatures are generated within the engine. Forward speed is, however, reduced, and thus airflow to the engine is also reduced. In this type of situation, the pilot should be aware of the possibility of overheating. Climbing at the best rate of climb speed for your type of aircraft is preferable to prolonged use of the best angle of climb speed. In the cruise at altitude, because the drop in air temperature at height will improve the efficiency of the cooling system, the cowl flaps may be partially closed to maintain the engine temperature. Descending can also cause problems. Engine power is reduced and thus less heat is generated. If the aircraft is put into a dive, this will increase the flow of air over the engine and increase the possibility of overcooling it. The sudden change in temperature thus caused is known as thermal shock. Thermal shock, which can cause engine components to fracture, happens most commonly in both the cylinders and the cylinder heads. Improved control of engine temperature, which would minimize the occurrence of thermal shock, is possible where cowl flaps or gills are fitted, but these items may not be available on many light aircraft. On these aircraft, the pilot can control the engine temperature by either manipulating the airspeed, the engine power, or the mixture control. In descent, the cowl flaps are closed in order to reduce the cooling effect of the airflow. It can also be beneficial to periodically apply engine power for short intervals during the descent. The length of time that high-power settings are used on the ground should normally be limited, as the only cooling effect available is the propeller slipstream. This may not always be sufficient, and overheating can occur, especially on hot and high airfields. Both cylinder head temperature and oil temperature should be closely monitored during ground running. The engine oil temperature is particularly important because of the fact that engine components, such as the pistons and bearings, are cooled by the lubricating system. Prior to shutdown, the engine should be run at idle power for a short period until engine temperatures have reduced and stabilized. Shutting down whilst the engine is very hot can result in uneven cooling and possible damage through distortion of the components. This concludes the lesson on cooling.